going to talk about how to choose if it's linear, quadratic, or an exponential model. So you can have a linear, a quadratic, or exponential functions to model some sets of data. If it's linear, you know you're dealing with y equals mx plus b, and it looks like this. It's a line. If it's quadratic, it's going to be in the form ax squared plus bx plus c, and it's a parabola, or a big U. If it's exponential, it's in the form y equals a times b to the x, and it's half of a parabola, or half of a U. All three of these are now graphs that you should be familiar with. I should not be telling you any new information. So, linear, quadratic, exponential. So how do you know? So let's say you're given sets of points. You can always plot the points and graph them to determine what they are. So looking at the points in graph A, if I plot them over 3f6, negative 2, 2, 0, 2, 3, 6, 1, negative 1, I missed one there, and 2, 2, and then I connect them, you will see this gives me a parabola. So this is going to be a quadratic. Okay, if we look at these, we go over 2 up 5, over 0 up 3, over 1 up 2.5, over 2 up 2. We come here, if you look at these, they are not in a line. They're going to keep going like this. So this is an example of exponential. Okay, so quadratic because it's a parabola, exponential because it's got that kind of boomerangy shape. And then over here, if you connect all of these, you should get a line. Now, keeping in mind that I did not draw these on graph paper, so none of them are perfect, but we would call this one linear. So again, one way to determine what they are is to simply model them by graphing. So plot the points that you have, connect the points, and see where do you end up. Okay? You could also analyze the data numerically. You don't always get to graph it. You could, but sometimes that takes longer. So looking at this first set of points, over here you can very easily see they're separated by just 1. Over here, you see that everything has a very even distribution of 4. If you went through, you could probably find a slope. So there's a common difference of 4, therefore this is linear. So when it's linear, the first set of differences are going to be the same. And you'll see what I mean by first in just a second. But so the very first time we looked for the difference, it was all 4, therefore this is linear. And if we graphed it, you know that it's going to look like this. Could possibly go the other way, but in any case, it's going to be a straight line. Now looking here, again, the x values are all 1 apart. Look at the y values. The first time, they're all over the place. Negative 14, negative 4, plus 6, plus 16, plus 26. There's no way to find a relationship right there. But if we look here, the next time, or the second common difference, this time the second common difference is all 10. So when the second common difference is the same, we say that it's quadratic. So in a quadratic, the second common differences are all the same. So linear, the first difference is the same. Quadratic, it's the second difference that is the same. Okay, so now we want to look over here. Again, our x values are each 1 apart, which is very typical. What's happening with the y? Times 3, times 3, times 3. So this time we have a common ratio of 3. It could be multiplied, it could be divided, but when we have a common ratio, then we know it's exponential. So in an exponential graph, you're looking at a common ratio. So linear, first difference, quadratic, second difference, exponential, you're looking at a ratio from one number to the next. Like I said, in this case, your ratio was 3. Everything was multiplied by 3. Okay, so here's where we put all this together. We're going to model the data. So here are our data points, and right here we're going to graph it. So when we graph this, if we look at it, I'm going to put this point a little lower. If I just look at it, it really looks like it's going to be exponential, right? Just looking at those dots, if I try to plot them, they really appear to be exponential. That's step 1. Just graph the data. Okay, so step 2. It appears exponential, so let's test for the ratio. So I'm going to go back. To find a ratio, take the second number and divide it by the first. Okay, because multiplying it in this case isn't going to work so well. So if I do 8 divided by 20, I get a ratio of 0.4. Well, does that work for all of them? 3.2 divided by 8, I get 0.4. So far, so good. 1.28 divided by 3.2, still 0.4. One more, let's see if it works. 0.512 divided by 1.28 is 0.4. So I can say that there's a common ratio of 0.4. So now I found my graph, I found the common ratio. This is definitely exponential. So I need to write a model. Remember that your graph or exponential form looks like this. So we're going to say A is our initial amount, and B is our amount of growth or decay, and we're going to put X up here. So we would say Y equals A. We're going to start with 8 because we're looking up here at this 8. We're putting it where X equals 0, and then our growth or decay is by 0.4 because that was our common ratio. So we could say that our equation for this would be Y equals 8, because that's our starting point, times, or I can even just put it like this, 0.4, because that was my common ratio, that was my amount of growth. Each time we're actually, in this case, it's decay because it's less than 1, so to the X, okay? We would put each one of those in there to find out how much does it grow. So this would be your model. And that's how you would model your data based on what you have. But you could do this with any kind of data. You could make it for an exponential or a quadratic or a linear function.